Hello there, and welcome to the Sleepless Scientist, where curiosity gets cozy and science takes the scenic route to slumber. I'm so glad you've arrived. Maybe you're already tucked beneath the covers, maybe you've curled up on the couch, or perhaps you're simply searching for a gentle companion while the night stretches on. Wherever you are, this is your quiet corner. Tonight, we'll wander slowly into one of the most surprising truths the universe offers. That time itself does not always flow the same for everyone. Before we set out, I'll ask something small. If you find comfort in these calm explorations, you're welcome to tap the like button or subscribe. It helps this sleepy little community grow. And if you feel like sharing, leave a comment with where you are and what time it is for you right now. It's always a joy to see how scattered and yet connected we are, each listening in our own slice of time. Now, soften the room, perhaps dim the lights, maybe let a fan hum in the background if you like, and if your mind drifts during our journey, that's perfectly fine. Let it wander, the story will still be here. So let's begin. Imagine a train platform in the late evening. A clock hangs overhead, ticking softly. On the platform, a passenger stands still looking up. On the train that rushes past, another clock ticks, mounted above the seats. Both clocks look ordinary, both hands sweeping forward in steady rhythm. Yet here is the curious thing. For the observer standing still, the moving train's clock will actually run slower. Not just appear slower, but truly tick more gently, as if time itself was stretching inside that train. This was not a magician's trick, nor an illusion caused by tired eyes. It is one of the quiet consequences of Einstein's theory of relativity, a consequence so startling that even today it can feel more like a parable than physics. A moving clock truly does run slow compared with one at rest. That is the puzzle we'll cradle tonight. If time can bend like this, slowing for one, flowing faster for another, what does it mean for satellites orbiting high above us? For the heart of a black hole where time nearly halts, for the unfolding story of the cosmos itself. And perhaps most personally, what does it mean for you and your private sense of now? Our journey will not rush. We will take it step by step, each idea wrapped in an image you can hold without strain. We'll pass through quiet stations of thought, the foundations of Einstein's vision, the experiments that proved it, the technology that depends on it, and the mysteries it still leaves us with. At each pause, I'll offer you not heavy equations, but metaphors. Time as a river, time as stretched fabric, time as a companion that can walk more quickly or more slowly depending on which road you take. Already you may feel your mind leaning into that image of the river. Imagine it flowing steadily, but with hidden currents. In one channel, the water slides quickly, in another it lingers, pooling and eddying. Drop 2 leaves into the stream, one into the faster current, one into the slower, and when you look again, they will have drifted apart, though both swirled in what felt like the same water. Time, in Einstein's universe, is not the uniform stream Newton once imagined, but a river with varied flows. And though this sounds far away, something belonging to physicists, to astronomers, to chalkboards covered in symbols, it is not distant at all. It shapes the phone in your hand that tells you where you stand on a map. It explains why muons, those tiny particles born high in the atmosphere, survive long enough to reach the ground at your feet. It even dictates what an astronaut will carry back in their very body when they return from orbit. A heartbeat, an age, ever so slightly younger than yours. But before we step into satellites and stars, let us linger a little longer with the parable of the train. For the passenger inside, the clock seems steady. They sip their tea, turn a page, glance up, and see the second hand moving as always. For them, nothing unusual is happening. This is one of the strangest aspects of relativity. Inside your own experience, time always feels ordinary. It is only when compared with another frame, another traveller, another height, another speed, that differences show. It is as if each of us carries a private metronome. To To us it is perfect, steady, always in tune. Yet when our metronome is set beside another, the notes do not align. One ticks more quickly, another more slowly, though each swears it is right. Time is faithful, but it is not universal. That realization can be unsettling, but also strangely comforting. It suggests that your moments, your laughter, your sighs, your pauses, are not merely fractions of some great cosmic stopwatch, but threads stitched into a personal path through space-time. You live not in an absolute now, the same for all, but in a private now, carried gently with you wherever you go. And so, as we set out into this story of time dilation, let's hold on to two simple things. First, that motion and gravity truly can alter the tempo of time, and second, that while the details may sound daunting, the truth itself is quiet. Time is flexible, not rigid, intimate, not mechanical. Tonight, we'll see why. So take a breath. Let your shoulders sink a little deeper. Ahead lies Einstein's groundwork, the weaving of space and time, the way light insists on being constant, and how, to keep its promise, the universe bends everything else. But we'll come to that in due course. For now, rest with the image of the train and the two clocks, one tick steady, one tick slow, both right, both real, both proof that time is more mysterious and more tender than we first imagined. Take another breath, and let your mind loosen a little more. We've stepped off the train platform where two clocks refuse to agree, and now we begin to ask why. What hidden rule of the universe makes one clock tick gently while another hurries on? The answer lies not in the clocks themselves, but in the stage on which they sit. To understand time dilation, we must first understand the fabric that holds both space and time together. For centuries, people thought of space and time as separate things. Space was the emptiness between objects, a kind of invisible box in which planets moved and apples fell. Time was a universal rhythm, ticking in the background, flowing evenly no matter where you were or what you were doing. Isaac Newton once pictured it like a grand stage. Actors came and went, plays unfolded, but the stage itself never shifted. Time flowed steadily and universally, indifferent to what played upon it. This view felt natural. When you drop a stone today and another tomorrow both fall the same way, surely time must tick the same for everyone. But the 19th century brought an unease to this picture. Scientists working with electricity and magnetism found that the speed of light seemed to disobey Newton's rules. No matter how you moved, whether toward the light or away from it, the beam always raced at the same speed. This stubbornness puzzled them. If you were on a moving cart and threw a ball forward, the ball's speed added to the cart's. Why didn't light behave the same way? Enter Albert Einstein, a young patent clerk with more questions than answers. He suggested something radical. Perhaps it isn't light that changes, but our very understanding of space and time. Instead of thinking of them as two separate tapestries, Einstein wove them together into one. The result was space-time, a single fabric that blends the three dimensions of space with the dimension of time. Imagine a vast quilt stretched out beneath the universe. On this quilt are embroidered the paths of stars, planets, and even your footsteps. Time is not a separate thread. It is woven directly into the same cloth as space. Every event, every moment, every position and tick of the clock has its place stitched into this four-dimensional fabric. And just as cloth can wrinkle, fold, or stretch, so too can space-time. Place something massive on the quilt, say a planet or a star, and the fabric bends beneath its weight. Smaller objects roll toward it, not because they are being pulled by an invisible hand, but because they are following the curve in the fabric. Gravity, in Einstein's picture, is not a force that tugs. It is the geometry of space-time itself. This weaving together of space and time has a curious consequence. If light must always move at the same pace, then space and time themselves must adjust to keep the promise. When you move faster, distances shrink and time stretches. The universe, in effect, rearranges the weave so that light never breaks, its rule. Think of it as an orchestra that insists one violin always keeps perfect pitch. To accommodate that, the other instruments must subtly retune. Time itself bends in order to keep the music consistent. It may help to picture space-time not as a stiff cloth, but as something alive and responsive, like a waterbed under pressure. Place a ball on one corner, and ripples travel outward. Lie down across it, and you feel the dips and slopes shift beneath you. Space-time is supple in this way. It moulds to motion and mass, ensuring the speed of light remains constant, a faithful guardian of cosmic rhythm. What makes this idea even more remarkable is how ordinary it can feel in your daily life. You don't notice space-time bending as you walk to the kitchen or ride a bicycle. At those gentle speeds, the distortions are vanishingly small. But scale things up, race a particle close to light speed, or let a star collapse into a black hole, and the bending grows impossible to ignore. Time itself stretches, a second for one observer becoming minutes or years for another. Einstein's insight was not only profound, but oddly comforting. It showed that the universe is not governed by separate, rigid laws for space and time, but by a unified dance. Space cannot be stretched without time being stretched too. They are partners, inseparable, moving in step. You might imagine space-time as a grand cosmic loom. On this loom, galaxies and atoms are threads, woven in patterns that extend across billions of years. Light traces through them like a shuttle, never changing its pace, no matter how the loom turns. And you, sitting quietly in your room tonight, are part of that same weave, a single thread winding steadily along. To sit with this thought is to feel a kind of calm awe. The universe is not a stage we act upon, nor a stopwatch ticking in the background. It is a fabric, continuous and all-embracing, that holds us close, bends with us, and carries our private now as gently as it carries the orbit of Jupiter or the spin of a distant galaxy. So the next time you glance at a clock, imagine it not floating in empty space, but fastened to this subtle fabric. Its hands don't merely sweep through air, they trace a path in space-time itself. And when we ask why two clocks on two trains may disagree, we are really asking how their threads weave differently through that fabric. In the sessions ahead, we'll see how this weave explains both the slowing of moving clocks and the stretching of time near massive stars. For now, hold the image of the fabric close, pliable, vast, stitched with every second you've ever lived. A fabric that can ripple, curve and stretch, yet still cradle you softly within its folds. Take a moment to let your thoughts drift. We've been picturing space-time as a great fabric, supple and patient, curving under the weight of stars, stretching gently when things move quickly. But there is still a question hanging in the air like a lantern above a quiet street. Why light? Why is it this particular thing, this thin and bright thread, that sets the pace for the universe? Why not sound or stones or some deeper vibration hidden from our eyes? The story begins with a different kind of weaving, the weaving of electricity and magnetism. In the 1800s, James Clerk Maxwell gathered what were then scattered insights into how electric charges and magnetic fields behave. He wrapped them into a set of equations, elegant and quiet, that described how waves of electricity and magnetism ripple through space. And tucked within those equations, like a secret melody inside sheet music, was a number. That number was the speed at which those ripples must travel. When Maxwell calculated it, he discovered something astonishing. The number matched the speed of light. In that moment, light revealed its true identity. It wasn't some mysterious independent entity. It was a wave of electricity and magnetism intertwined, feeding each other as they moved. You can imagine it as two dancers holding hands. The electric field pushes the magnetic field. The magnetic field pushes back, and together they skip across the emptiness at a fixed tempo. The tempo was so exact, so insistent, that nothing seemed able to alter it. That discovery transformed light from an everyday experience into a cosmic anchor. Light was no longer just the glow of the sun or the flicker of a candle. It was the universe whispering its most stable rhythm. And this rhythm was not like others. Water waves change speed depending on depth. Sound speeds up or slows depending on air or wood or water. But light's wave refused to play that game. No matter the medium, or even in the absence of medium altogether, it held to its one pace. Scientists puzzled over this. Surely light must need some background to ripple through, the way sound needs air. They imagined an invisible ether filling the cosmos, a hidden sea through which light's waves rolled. For a while, this ether seemed as reasonable as anything. But then came the experiments. In 1887, Albert Michelson and Edward Morley built a clever device to measure light speed from different directions, hoping to detect Earth drifting through the ether. What they found was silence. No matter how they arranged their mirrors, no matter which way the Earth moved, the speed of light refused to change. It was as if light cared nothing for Earth's hurry around the sun. It carried its own clock, its own stride, independent of the ground beneath us. For Newton's universe, this was troubling. But for Einstein, still years away from publishing his theories, it was a clue that the stage itself was wrong. Light's constancy meant that the stage of space and time had to bend around it, not the other way. When Einstein finally stepped forward in 1905, he placed this stubbornness of light at the heart of his theory of special relativity. He declared, the speed of light is the same for everyone, no matter how you chase it or flee from it. And if that is true, then lengths must contract and time must dilate to preserve the rule. In other words, to keep light faithful, the universe reshapes itself. Imagine it this way. You and a friend both agree to meet a bird in the sky. The bird insists it will fly at exactly 10 wing beats per second, never more, never less. If you run toward it, you must adjust your step so that the bird still feels 10 beats away. If you lag behind, you must lengthen your time so the rhythm still fits. The bird refuses to compromise, so the two of you must. Light is that bird. The universe is its partner dance floor. This constancy explains why time dilation is not optional, not an oddity. It is the only way the universe can honour light's demand. Without it, we would have contradictions everywhere, beams that outrun each other, flashes that arrive out of sync. With it, everything remains harmonious, even if it bends our intuition. You might wonder, why this speed? Why 300,000 kilometers per second? Why not slower or faster? Physics can only shrug gently. The equations tell us it must be so, but not why. Perhaps it is simply the number stitched into the fabric, as unavoidable as the colour of leaves in spring. To contemplate it is like asking why the violin string sings in one note rather than another. The note is simply the one the string was tuned to. And so light stands as the great anchor in the sky. It defines what is possible, what is reachable, what counts as cause and what counts as effect. Its beams thread the cosmos, carrying messages from galaxies across billions of years, never bending their tempo, never yielding to impatience. For you, sitting in your quiet corner tonight, this constancy may feel abstract, yet it is in your room as surely as the glow of a lamp. When your phone tells you the time, it relies on signals racing at light speed. When you look at a star, the beams that reach your eye have travelled faithfully, each second, each kilometre at the same tempo. You're not simply looking at light, you're looking at the rhythm of the universe itself. And so, as we step further into this journey of time dilation, hold close this truth. Light will not bend its pace. Instead, the universe bends around it. time and space yield so that light may remain steady. That yielding is what stretches seconds on fast trains, what slows clocks in orbit, what makes gravity heavy not only on your feet but on your minutes. It is the quiet contract written into space-time itself. A head will walk more closely with that contract, will follow clocks set in motion and see how their seconds lengthen. Will meet twins who part and return, changed by the roads they chose. But all of that flows from the same anchor. Light, unyielding, carrying the steady beat that keeps the cosmic symphony in tune. Picture yourself holding a flashlight on a dark road at night. You press the switch and a beam leaps forward, a clean spear of light that seems to vanish into infinity. Now imagine running after it. Instinct whispers that if you run fast enough, perhaps you could keep pace with that beam, the way you might sprint alongside a friend pedaling a bicycle. But the universe has other plans. No matter how fast you run, that beam races ahead at the exact same speed. Run faster, and it still slips away. Launch yourself on a jet, a rocket, even the most advanced starship our imaginations can design, and still the beam never slows. This stubbornness is what Einstein grasped with such clarity. If light's speed is absolute, then something else must give way. And what gives is not the beam, but you. Your lengths contract, your time dilates, your seconds stretch so that the rules remain intact. It is as if the universe whispers, the light shall not change, so you must. Let's return to the light clock, one of Einstein's favourite mental toys. Imagine two mirrors facing each other, a pulse of light bouncing between them like a tennis ball in a slow volley. To the passenger who carries the clock, the light ticks straight up and down, marking each second with a soft, steady bounce. But if you stand on the platform watching that passenger's train pass by, you see the beam travelling not just up and down, but diagonally forward, like a bee zigzagging as it follows the train's movement. That diagonal path is longer than the straight bounce. Since light cannot move faster than its fixed speed, the only way to complete the longer journey is for more time to pass. To you on the platform, the passenger's clock ticks slower. This is the essence of velocity-based time dilation. When something moves quickly, the geometry of space-time stretches the intervals of its own clock. Each bounce of light takes longer, each tick lingers, and so time itself runs more gently. It is tempting to think of this as an illusion, a matter of perspective, but it is real in the deepest sense. When the train slows, the passenger emerges genuinely younger than you, even if only by a fraction of a second. Both clocks, when placed side by side again, will not agree. The moving one has experienced fewer ticks of time. To feel this without mathematics, imagine you're walking through rain. If you stand still, raindrops fall straight down upon your umbrella. But if you start walking, the drops no longer fall vertically. They streak at an angle, striking your front. The distance each drop must travel through your umbrella has changed. Something similar happens to light in motion. It must take a longer path, and the cost is time. And here is the profound symmetry. For the passenger on the train, it is you on the platform whose clock runs slow. They look out the window and see your time stretching, your seconds lengthening. Both are correct, because each is measuring time along a different path through space-time. Relativity tells us that there is no universal referee, no absolute now. Time is personal, woven to the journey itself. This may sound like a trick of language, but experiments confirm it. Particles called muons, born high in the atmosphere when cosmic rays strike, decay in mere millionths of a second. They should never survive the trip to Earth's surface, and yet we detect them constantly. Their flight is long only because, in their own rushing frame, time has slowed enough to let them live. If their seconds stretched, our meters contracted. Both stories are true. Velocity-based dilation shows us a strange generosity in the universe. The faster you move, the more time you are granted compared with those who remain still. For astronauts, this means that journeys near the speed of light would let them travel years into the future of Earth, while experiencing only months. Science fiction often plays with this, painting tales of voyagers who return to find centuries past. But at its heart, it is not fiction at all. It is the natural consequence of chasing beams. To hold this gently, think of time not as a fixed clock on the wall, but as a thread you carry with you. Walk slowly, the thread unrolls at a steady pace. Rush forward, the thread slackens, stretching out, giving you fewer ticks for the same distance. Everyone carries their own spool, and no two spools unwind in quite the same way once motion divides them. Even though our everyday lives move far too slowly to notice these changes, they are there. GPS satellites, hurtling through orbit, feel the slowing of their seconds. Airplanes, though only shaving microseconds, still step slightly out of sync with the ground. The differences are tiny, but they are the same law that governs particles in accelerators and explorers at near light speed. Among the many parables of relativity, none has captured the imagination more firmly than the story of the twins. It is told so often that it feels almost like a fairy tale. Two siblings born on the same day, sharing the same laugh, the same lullabies, the same childhood, until one of them climbs into a spacecraft. That sibling departs Earth and sails through the cosmos at speeds that brush the edge of light, while the other remains at home. Years pass. Eventually the traveller returns, and when the two embrace again, they discover that their ages no longer match. The one who flew is younger, while the one who stayed behind has lived through more years. This is the so-called twin paradox, though paradox is the wrong word. A paradox is a knot that cannot be untied, a puzzle without resolution. In this case, the knot is real, but the threads do come free. What looks at first like a contradiction is in fact a careful lesson about how time bends under motion and acceleration. Let's walk through it slowly. Imagine the twins standing together before departure, their watches ticking in unison. The traveller boards the rocket. Engines roar, and the ship accelerates outward, leaving Earth behind. For the twin on Earth, the traveller's time seems to run more slowly, stretched by velocity. The rocket's clock ticks more gently. The traveller's heartbeat lags compared to the pulse felt on the ground. But here's the subtlety. For the twin in the rocket, the story seems symmetrical at first. Looking back at Earth, they too see the planet receding, its clocks ticking slowly. If each sees the other's time stretched, then who is truly younger in the end? That is the heart of the question. The answer lies not in who is moving faster, but in who changes their motion. The earthbound twin remains in one reference frame the whole time, steady in the planet's slow rotation around the sun. The traveller, however, must accelerate, first to depart, then to turn around, and once more to return. These periods of acceleration break the symmetry. The twin in the rocket does not travel a straight line through space-time, but a bent one, curving away and then back. And in relativity, the straight path through space-time, the one that looks like rest, is the path of maximum time. The curved path, by contrast, yields fewer ticks of the clock. Think of two hikers beginning in the same valley. One remains in place, perhaps tending a fire, watching the river flow by. The other sets off up a winding trail, climbing steep switchbacks, circling around the mountain, and eventually returning to camp. Both experience the same dawn and dusk, but when they compare journals, the one who hiked has fewer entries. The path through the mountains was longer in distance but shorter in proper time. Relativity turns that hiker's effort into a subtle youthfulness. To ground this in imagery, imagine space-time as a vast sheet of silk stretched before you. Every journey is a thread drawn across it. The homebound twins' thread is nearly straight, a quiet line along the silk. The traveller's thread, however, bends outward, arcs away, and then folds back. When the two threads meet again, one is longer in the fabric's measure, and that longer one belongs to the twin who stayed. The rocket twin has traced a shorter arc through space-time, and so they have lived fewer seconds. This difference is not imaginary. If one were to measure the atomic decay of particles inside the rocket, or the number of heartbeats recorded by a monitor, the counts would come up smaller. When the twins meet again, the result is not a mere trick of perspective. One is genuinely younger than the other. And though we do not send humans yet at such speeds, nature performs the experiment for us. Muons in accelerators, like the travellers of the particle world, live longer than their stationary cousins. Astronauts circling Earth experience minuscule versions of the same effect, returning nanoseconds younger than they would have otherwise been. The paradox dissolves under the light of these examples. Acceleration matters, space-time geometry decides, and clocks keep their promises faithfully, even when their stories diverge. What makes the twin tale so enduring, perhaps, is not just the physics, but the emotion it evokes. Two siblings embrace, only to find that time has been uneven in its generosity. It suggests that time is not a single blanket draped over everyone, but a quilt stitched differently for each path we take. One might linger in a familiar room, another might race across the stars, and when they meet, their hours do not align. For us, sitting quietly tonight, this is less a riddle than a reminder. Every journey has its own tempo, every path its own unfolding of seconds. The traveller and the one who stays are not in disagreement. They have simply lived by different clocks, woven from the same fabric, stretched in different ways. So the paradox is no paradox at all. It is the universe showing us that time is personal, private, tied to the road we walk. In the sessions ahead, we will see how this truth deepens, how the mathematics behind it can be softened into gentle intuition, and how experiments have confirmed again and again what the story of the twins first revealed. So the next time you shine a flashlight, picture yourself sprinting after that beam. No matter how fast you go, the light always wins, not because you are slow, but because the universe bends your own seconds to protect its rhythm. Time dilates not as punishment, but as harmony. The tempo of light is fixed, and the orchestra of the cosmos retunes itself so the music stays in tune. This is why moving faster makes you slower, not sluggish, but younger. A gift of seconds, stretched thin, quietly offered whenever you chase the beams. By now, you may feel the rhythm of relativity settling in. Clocks that disagree, twins who meet again with different ages, beams of light that refuse to adjust their stride. Beneath these stories lies a single number, a quiet multiplier that tells us exactly how much time stretches or how much space contracts when things move quickly. This number is called the Lorentz factor, and though it comes wrapped in symbols, its meaning can be told in a way that doesn't require chalkboards or algebra. Think of it as the ruler by which the universe measures how bent the fabric of time has become when motion speeds up. The symbol for the Lorentz factor is the Greek letter gamma, a curving shape that itself looks a little like a ripple or wave. In equations, it is written as gamma equals 1, divided by the square root of 1 minus velocity squared over the speed of light squared. That is the technical form, but let us unwrap it gently. Imagine it as a scale that begins close to 1 and stays there for almost all ordinary speeds. Walk across your room, drive down a quiet street, fly in an airplane, and gamma clings tightly to the value 1 as if nothing has changed. Time dilation exists for you in those moments, but it is so tiny that you would never notice. Yet gamma is not content to remain near 1 forever. As speed rises, it begins to swell. Push yourself to 1/10 of the speed of light, something no human has yet managed but that our particle accelerators grant easily to subatomic travellers, and gamma stretches ever so slightly beyond 1. At half the speed of light, it grows larger still, about 1.15. At 90%, it swells to more than 2, and as you edge closer to light speed itself, gamma shoots upward like a balloon that refuses to burst. approaching 99.9%, it soars into the tens and hundreds. At the very brink, as you lean against the barrier of light speed, gamma would rise toward infinity. What this number tells us is simple, even if its form seems ornate. The faster you go, the more stretched your time becomes compared with someone at rest. A gamma of 2 means your clock runs at half the rate of another's. A gamma of 10 means 1 second for you is 10 seconds for them. The scale rises without mercy, demanding more and more energy to add each small slice of speed. You might think of it like climbing a hill. At first the slope is gentle. You walk without strain, barely noticing the incline. But as you climb higher, the hill grows steeper, and every step demands more effort. Near the top, the slope becomes nearly vertical. No matter how strong you are, you cannot reach the summit, because the hill stretches upward into the sky without end. The speed of light is that summit, forever out of reach. Gamma is the slope itself, warning you how much harder each step will be. Or picture it as a bellows, folded tight at rest. At low speeds, the folds remain close, hardly opening. As speed rises, the bellows stretch wider and wider, letting more air in, showing how time and space have dilated. Near light speed, the folds open so wide they seem endless, the bellows unable to close again. The Lorentz factor explains why energy demands for high-speed travel explodes so dramatically. Each increase in velocity is not just another mile per hour. It is a reshaping of space-time's fabric around you. To double your speed near the limit is not simply to push harder, but a fight against the geometry of the universe itself. It also helps explain why cosmic particles survive journeys they should not. A muon in the laboratory, living for microseconds, should never travel far. But with a gamma of hundreds in an accelerator, its lifetime stretches long enough to circle rings of magnets, to dance through detectors, to paint its story across our instruments. Time is not cheating. It is simply flowing differently for the particle. For you listening tonight, perhaps with your eyes growing heavy, the details of the formula may drift away, and that is perfectly fine. What matters is the image, a number that begins as 1, steady and small, but that swells larger and larger as speed increases. A scale that shows us how time bends more dramatically the faster you move. You might imagine gamma as a lantern you carry. At slow walks it glows, faintly, unchanged. As you begin to run, the light brightens just a little. Push harder, and it shines more. Near the speed of a light, the lantern blazes like a sun, pouring out brilliance that cannot be hidden. The glow is the measure of how much your seconds differ from another's. What is soothing, perhaps, is that this rule is absolute and consistent. The Lorentz factor does not play favourites. It treats particles in accelerators, satellites in orbit, and travellers on trains with the same impartial care. For all of us, it whispers the same thing. Your time is yours alone, unfolding at a pace tied to your motion through the fabric. And yet, despite its universality, gamma remains invisible to us in everyday life. You will never notice it as you stroll down a street, never feel it stretch as you bicycle through a park. It is there, humming beneath your seconds, but so minuscule that it hides from all senses. Only when speeds soar, when the cosmos accelerates its smallest messengers, does gamma show its brilliance. So, if you ever hear of the Lorentz factor and feel daunted by its symbols, remember this. It is nothing more than a ruler, telling us how much the fabric stretches when we move quickly. It is a balloon swelling, a hill steepening, a bellows opening, a lantern brightening. It is not a monster of mathematics, but a gentle measure of how the universe keeps its promise to light. By now we've wandered through clocks on trains, through twin stories, through the quiet swelling of the Lorentz factor, and perhaps you feel that these ideas belong mostly to thought experiments, the kind of puzzles that philosophers and physicists sketch in notebooks. But time dilation is not merely a tale told in the lecture hall. It is written into the sky itself, raining down on us every day in the form of particles that live longer than they have any right to. High above you, even now, cosmic rays are striking the upper layers of Earth's atmosphere. These are not gentle visitors. They are particles born in violent corners of the universe, supernova remnants, black hole jets, regions where magnetic fields lash and fling atoms into space at near-light speeds. When these wanderers finally crash into our atmosphere, they trigger showers of secondary particles. Among these are muons, cousins of the electron but heavier, unstable, fleeting. In laboratories, a muon lives on average just 2/millionths of a second before decaying into other lighter particles. 2/millionths of a second. It is a blink inside a blink, so short that at ordinary speeds a muon could hardly travel more than a few hundred meters before vanishing. Yet here they are, at the surface of the Earth, streaming through the air, through stone, even through you. Thousands of them pass through your body every minute as you sit here listening, and they should not be here at all. From the moment of their birth, high in the atmosphere, they face a journey of tens of kilometers downward. By the calendar of Newton's world, they would never make it. Their brief lifetime would expire long before they touch the ground, and yet detectors show them arriving, abundant, undeniable. The explanation lies in the stretch of time under high velocity. These muons are travelling at speeds close to the speed of light, with Lorentz factors in the tens or hundreds. In their own frame, their lives still last just microseconds. But to us, standing on Earth, those microseconds have been stretched into tens or even hundreds of times longer. Their clocks run slower compared with ours, giving them the grace to complete the journey. It is a quiet, beautiful proof of relativity. Particles from space living long enough to reach us only because their time is dilated. If time were absolute, as Newton once believed, the ground would remain untouched by these particles, and our detectors would be silent. Instead, they chatter constantly, whispering that time is not what we thought. You can imagine each muon as a traveller handed a strange gift. In its own perspective, the trip to Earth is short, only a few kilometres perhaps, because to a particle moving near light speed, distances themselves contract. To us, the particle seems to fly through many kilometres of air and survive for far longer than its nature should allow. Two views, two stories, both true, reconciled by the bending of space-time. Laboratories have confirmed this again and again. In accelerators, where beams of particles are whipped into rings near light speed, lifetimes stretch visibly. Mesons and muons that would normally decay in fractions of a microsecond circle the magnets again and again, giving experimenters time to study them. The equations of relativity, once ink on paper, here become a tangible tool. Without time dilation, particle physics would be impossible, the very building blocks of matter decaying before they could be observed. It is humbling to realize that the evidence of time dilation is not hidden in distant galaxies or rare astronomical alignments, but falling softly on us every moment. The air you breathe, the stones underfoot, the walls around you, all are quietly threaded by these rushing travellers. You do not see them, you do not feel them, yet they are there, carrying with them the proof that time bends. Sometimes scientists call muons nature's gift to relativity, because their very survival to the Earth's surface is a daily natural experiment. It is as though the cosmos decided to provide us with a demonstration, not in chalk but in rain, particles falling like faint reminders that the universe is stranger and more generous than we first assumed. If you could picture these muons with gentle imagination, you might see them as glowing sparks falling through the atmosphere, each one a tiny lantern with a fuse too short to reach the ground. And yet, as they rush, the universe lengthens their fuse, stretches their seconds and lets them arrive at your doorstep. Without time dilation, their glow would fade in the upper air. With it, they descend all the way to you, silent but faithful. This is what makes relativity feel less like abstraction and more like presence. You're not separated from these truths by distance or theory. They flow through you quite literally. If you place a detector in your living room, you will hear the clicks of muons announcing their passage, each click a second stretched, a life extended, a gift of time. And perhaps there is comfort in knowing that even fleeting things can endure when motion bends their clocks. The muon, destined to vanish almost as soon as it appears, finds new life in speed. What seemed fragile becomes resilient, not by defiance, but by the patient laws of the cosmos. Time, usually our strictest master, here reveals itself as merciful, willing to slow down for the smallest of travellers. So when you think of time dilation, do not imagine it only as an equation or a faraway puzzle. Imagine instead the quiet rain of particles, unseen but constant, threading through your evening. Imagine their brief sparks extended, their journeys completed, their lives lengthened by the very fabric of space-time. Each one a reminder that motion does not simply move you through space, it reshapes the rhythm of your time. Let's imagine, for a moment, that time is not an invisible stream flowing evenly everywhere, but a landscape that you can walk through. In some places the ground is flat, in others it slopes downward into valleys, and in still others it rises into hills. Walking across flat ground feels normal, your steps steady and easy. But walk down into a valley, and every stride feels just a little heavier, slower, drawn out. This is what Einstein suggested when he explained that gravity does not merely tug on objects from afar. It shapes the very fabric of space-time, creating valleys where time itself runs thick and slow. For Newton, gravity was a force, a steady pull between masses, binding planets to stars and apples to Earth. It worked well for centuries, predicting orbits and tides, making sense of falling stones and swinging pendulums. But Einstein's insight in 1915 reimagined gravity entirely. He said that mass and energy curve space-time, and that objects, including you, me and our clocks, must follow the paths carved by that curvature. To stand near a massive body is to stand deeper in a well of time. You may wonder what that means for something as ordinary as a clock. Imagine two identical clocks, one resting on a mountaintop, the other down in a valley. Both are perfect, their gears flawless, their pendulums steady, or in the modern case their atoms vibrating with impeccable rhythm. You might expect them to remain in lockstep, tick for tick. Yet Einstein's equations say otherwise. The clock in the valley, closer to Earth's mass, will tick more slowly than the one at the mountaintop. To the person standing with the lower clock, time feels normal. They brew tea, glance at the ticking seconds, and nothing seems amiss. But compare the two, and the valley's clock has lagged just slightly, as if time itself were syrup flowing more thickly in the lowlands. This is gravitational time dilation. The stronger the gravity, the slower time moves. And though the difference is small here on Earth, mere nanoseconds for clocks separated by mountain heights, it is real, measurable, and confirmed in laboratories with atomic clocks so sensitive they can register differences in altitude of just a few centimetres. In those tiny gaps, time runs measurably faster above your head than at your feet. The imagery of a hill or valley of time is not just poetic. In Einstein's picture, it is literal geometry. Space-time bends around mass, and that bending alters the rate at which time unfolds. Light climbing out of a gravitational well loses energy, stretching to longer, redder wavelengths. This effect, known as gravitational redshift, is another expression of clocks ticking more slowly in deeper wells. To a distant observer, the signals from a low-lying clock appear stretched out as if the clock itself had become sluggish. To hold this more concretely, imagine a ball rolling across a trampoline. Place no weight on the trampoline and the ball travels in straight lines, crossing without difficulty. Place a heavy stone in the centre and the fabric sags, pulling the ball into curved paths. But the sag does more than bend the ball's route. If you could place a clock on that sagged fabric, it would tick slower, Every swing of its pendulum, every vibration of its atoms stretch just a little. The sag is both a curvature of space and a slowing of time. They are one phenomenon described two ways. This idea can feel remote when spoken of in terms of mountains and valleys, so let us shrink it down to your body. Right now, your head is farther from the Earth's centre than your feet. By Einstein's rules, the seconds at your head pass ever so slightly faster than those at your feet. The difference is absurdly small, trillions of times too tiny for your senses, but it is there nonetheless. You're a tower of stretched time, your seconds flowing a little unevenly along your height, stitched together so smoothly that you never notice. Where gravity grows stronger, these differences grow dramatic. Near a neutron star, where mass is squeezed into a city-sized sphere, time runs markedly slower on the surface compared with distant space. Near a black hole, the effect becomes extreme. To a distant observer, a falling object's clock appears to grind to a halt as it approaches the horizon. To the falling object itself, time feels normal, steady, uninterrupted. Two stories, both true, both born of curved space-time. Gravitational dilation is not just a curiosity. It matters for the satellites that guide your phone. It matters for scientists interpreting signals from stars and galaxies. It matters for the story of the early universe, when everything was denser and clocks ticked differently across the young cosmos. But we will come to those in later sessions. For now, rest with the image. Time is not flat and universal, but a landscape shaped by gravity. Each mass creates a valley, and each valley thickens time's flow. When you next climb a hill or descend a staircase, let it remind you. Your seconds, too, are shifting slightly. Higher is faster, lower is slower. To live on Earth is to float forever inside a gentle basin of time. It is a basin so shallow we hardly feel it, yet without it, planets would not orbit, galaxies would not cohere, and our seconds would not belong to us in the same way. Einstein's reimagining of gravity gave us not just a new theory, but a new vision of the universe. We are not simply pulled downward by an invisible tether. We are carried along paths traced by curved space-time, living out our seconds in landscapes where time is thick or thin. To see gravity this way is to see time itself as a living terrain, shaping and shaped by the stars. If the thought of time flowing differently in mountain valleys and star-forged chasms feels distant, let us draw it closer to your daily life. The bending of time is not something that waits for neutron stars or black holes. It is happening quietly in the sky above you, in satellites no larger than a van, circling Earth like patient caretakers. Each of them carries a clock, and without Einstein's corrections, your morning walk to a cafe might end on the wrong street, your rideshare might stop in the wrong lane, and planes might drift far off course. These satellites form the Global Positioning System, or GPS. Each one orbits more than 20,000 kilometres above Earth, moving at about 14,000 kilometres per hour. Inside, atomic clocks tick away, their vibrations measured and shared with receivers on the ground. Your phone listens to 4 or more of these satellites at once, triangulating your position from the signals. But there is a problem, a very subtle, very persistent problem. Left on their own, those satellite clocks do not agree with the clocks on Earth. Two forces are at play. First is motion. The satellites rush through orbit, and by the rules of special relativity, moving clocks run slow. Their seconds stretch compared with ours. Second is gravity. In orbit, the satellites are farther from Earth's centre, floating higher in the gravitational landscape. Time there runs faster than time in the valley of the Earth's surface. The two effects pull in opposite directions. Speed drags the seconds back. Weaker gravity nudges them forward. And when both are accounted for, the net result is that satellite clocks run faster than ours by about 38 microseconds every day. 38 microseconds. A blink within a blink. Smaller than anything your senses could grasp. Yet in the delicate world of GPS, this is enormous. If the difference were left uncorrected, positioning errors would grow by kilometres each day. A system meant to guide hikers through forests and plains across oceans would quickly collapse into nonsense. So engineers, taking Einstein at his word, corrected for relativity. The clocks were pre-tuned, ticking slightly slower on the ground so that once in orbit they matched Earth's rhythm. Ground stations monitor them constantly, adjusting for the ceaseless drift. The result is that you, standing on a sidewalk, can open your phone and see a blue dot hovering almost exactly where you are. Without relativity, you would be lost, perhaps by the width of a city. With relativity, the world feels mapped and manageable. There is something humbling about this. The ideas that once seemed philosophical curiosities, the stretching of seconds, the bending of space-time, are now built into the very fabric of our technology. Every time you check directions, you are leaning on Einstein's equations. Each small correction to a satellite clock is a whisper from relativity, reminding us that time does not flow equally everywhere. Airplanes too provide a stage for this quiet drama. When a jet arcs across the sky, carrying passengers and their watches, time for those travellers runs differently than for the people waiting in terminals below. The effect is small, a few nanoseconds over a long flight, but measurable. In the 1970s, physicists carried atomic clocks aboard commercial flights circling the globe. When they compared them with clocks left behind, the differences matched Einstein's predictions. Eastward flights lost time, westward flights gained it. The details involved both special relativity, motion slowing the clocks, and general relativity, altitude raising them out of gravity's grasp. The two nudges combined into real, recorded changes, and in orbit astronauts feel this even more strongly. On the International Space Station, circling Earth every 90 minutes at speeds exceeding 27,000 kilometers per hour, time slows due to motion but speeds up due to altitude. The balance tips so that astronauts return to Earth ever so slightly younger than their twins below. The difference is tiny, measured in fractions of a second across months, but it is there. Their very bodies carry the stamp of relativistic time. It is almost poetic. To leave Earth's pull and to race above its surface is to slip just a little from its clock. The heartbeats of astronauts are recorded by a slightly different metronome. When they return, they bring back not only memories of floating and stars glimpsed through windows, but also proof that time is pliable. Their veins and bones, their very cells, have lived by a different tempo. For us, the implications are quiet but profound. Relativity is not locked away in laboratories or written only in textbooks. It threads through your daily commute, your phone's navigation, the safe arrival of airplanes, the careful timing of financial systems. If relativity were false, your world would be full of errors, maps useless, travel dangerous, satellites blind. Instead, the harmony of these systems is testimony to the bending of time. So the next time you glance at your phone's map and see that calm blue dot settle gently over your street, remember, this pinpoint is possible only because engineers bowed to Einstein's vision. They trusted that time runs thicker, closer to Earth, that motion stretches seconds thinner, and that the balance of the two must be accounted for. Your simple walk to a cafe is stitched invisibly to the deep geometry of space-time, and in that realization lies a certain comfort. The vast abstractions of physics are not distant. They guide you through your city. They return astronauts with stories in their blood. They carry airplanes across continents. They remind you that you are always walking in a landscape where time runs differently at every height, every speed, every orbit. Relativity, in this sense, is not an exotic visitor. It is your daily companion, quiet, precise, unseen, but faithful, and without it, your sense of place on this earth would dissolve. If satellites remind us that relativity is a quiet companion, then stars remind us that it can also be overwhelming. bending not just seconds but entire destinies of matter and light. To glimpse this, we turn our attention to the collapsed hearts of massive stars, neutron stars and black holes, where gravity grows so dense that time itself slows to a crawl. A neutron star is what remains when a massive star has burned its fuel, collapsed under its own gravity and halted just short of complete destruction. In that moment of collapse, atoms are crushed, protons and electrons merging into neutrons, until what was once a sun larger than our own is compressed into a sphere no wider than a city. The mass of several suns packed into a space you could drive across in an hour. Such a star bends space-time ferociously. Near its surface, clocks tick more slowly than in the emptiness far away. Imagine standing impossibly on that surface. To you, your seconds would feel ordinary. Your pulse, your breath, your heartbeat steady as always. Yet to someone watching from a distance, your signals would be stretched, your seconds longer, your clock delayed. Light escaping your vicinity would climb out of the gravitational well, losing energy, shifting into redder and redder hues. This is gravitational redshift, the glow of heavy stars bleeding toward crimson, not because the atoms themselves have changed, but because time runs differently where they burn. The image is haunting, a star so dense that even its light is slowed, drained of its colour as it climbs back toward the wider universe. Astronomers detect this redshift in X-rays and spectral lines, direct signs that time is thicker near these collapsed suns. For them, a neutron star is not only a monument to gravity but also to time's elasticity. Now take the thought further. Imagine not merely a neutron star but a black hole. Here the collapse goes to completion, space-time folded so tightly that nothing, not even light, can escape. From far away, the surface we call the event horizon becomes a strange mirror. Watch an object fall toward it, and you will see it slow, its signals stretching into longer and longer wavelengths, until finally it seems frozen, hovering at the edge. The object itself does not notice anything unusual. Its seconds tick as they always did, its heart still beats, its thoughts still form. But from your perspective, its time has slowed to nearly nothing. This is perhaps one of the most unsettling contrasts relativity offers. Two truths, equally valid, but irreconcilable in ordinary terms. From outside, the infailure halts forever, trapped in an endless descent. From inside, the journey continues naturally, crossing the horizon without drama. It is as if time were syrup for one witness, water for another, both tasting different from the same cup. These extremes may seem far from your nightly walk or morning commute, yet they are part of the same law that shifts satellite clocks by microseconds. It is the same bending stretched to its most dramatic. Gravity slows time. The heavier the mass, the steeper the curve, the slower the tick. Your feet are already a little younger than your head for this reason. Place yourself on a neutron star and the difference would be unmistakable. Stand at the brink of a black hole and the difference would be absolute. Astronomers sometimes describe the universe as a tapestry with two dominant threads: expansion, which stretches space, and gravity, which bends it inward. Where expansion dominates, galaxies drift apart, redshifts accumulate, time feels broad and patient. Where gravity dominates, in collapsed stars and black holes, time itself clings to matter, dragging seconds into molasses. The cosmos is not one tempo but many, each tied to the terrain of space-time beneath it. To hold this softly, picture yourself by a river. In some places it runs shallow and quick, water skipping over stones. In others it pulls deep and slow, eddies circling for long minutes before moving on. Time behaves the same way. Above Earth's surface, in orbit, it is the shallow stream flowing a little quicker. On neutron stars it is the deep eddy, circling slowly before it escapes. On the edge of a black hole the eddy never ends. And yet, From within your own stretch of river you never notice. Your seconds always feel like seconds. Your heartbeat never seems delayed. The slowing only appears when compared to another stream, another observer in a different bend of space-time. This is the quiet revelation of general relativity. Time is not universal, but local, personal, tuned to the valley or hill you inhabit. So the red glow of heavy stars is more than just an astronomical curiosity. It is a message from the universe that time is flexible, not rigid. It is the same message carried by satellites overhead, only amplified to cosmic scale. Like climbing away from a neutron star tells us that seconds there are stretched. A frozen image at the edge of a black hole tells us that time itself can pause, depending on where you watch. Next time you see a photograph of a pulsar spinning with metronomic flashes, or hear of a black hole bending the light of a distant galaxy, remember that you are also seeing time itself, slowed and reshaped. You're glimpsing the syrupy flow of seconds in deep gravity, translated into colours and delays that your telescopes can catch. And so, gravitational dilation is not only about equations or exotic stars, it is about the recognition that time is not evenly poured across the cosmos. It pools, it thins, it thickens, and it sometimes nearly halts, and all of it flows from the same fabric you inhabit tonight, the same fabric that carries your breath, your heartbeat, and the quiet tick of your bedside clock. By now, we have wandered through valleys of time shaped by mountains and neutron stars, and perhaps the story still feels like something distant, belonging to astrophysicists, satellites, or cosmic rays. But the proof of relativity has not only fallen from the sky in the form of muons, nor hidden itself in red-shifted starlight. It has also been carried deliberately around the world in the most ordinary of settings. Commercial airplanes humming softly across the globe, their cargo not just passengers and luggage, but some of the most precise clocks ever built. The experiment was performed in 1971, and it has become one of the most elegant confirmations of Einstein's strange ideas. It is known as the Haffel-Keating experiment, named after Joseph Haffel and Richard Keating, two physicists who wondered if they could catch time dilation in action, not in theory, not in space, but in the skies above everyday sitters. They secured 4 cesium beam atomic clocks from the US Naval Observatory, each one capable of keeping time with a precision unimaginable in ordinary watches. These clocks were then packed carefully into shock-absorbing cases and carried aboard commercial flights, first flying eastward around the world, then westward, before finally returning to their origin. Why east and west? Because relativity has 2 competing hands when it comes to time. One is special relativity. Motion slows a clock compared with one at rest. The other is general relativity. Altitude, and thus weaker gravity, speeds a clock compared with one closer to Earth's mass. By flying at cruising altitude, the clocks would run slightly faster due to reduced gravity, but by moving quickly relative to the ground, they would run slower. Eastward, the plane's speed added to Earth rotation, making the effect of special relativity stronger. Westward, the plane's motion opposed Earth's spin, reducing the relative speed and letting the gravitational effect dominate. It was a delicate balancing act, like listening to 2 instruments playing against one another, sometimes harmonizing, sometimes cancelling, sometimes letting one voice rise above the other. The result, when the clocks were carried, was not hypothetical, but measurable. After completing the trips, the airborne clocks disagreed with the ground-based ones by tens of nanoseconds, fractions of a second, yet exactly the discrepancies Einstein's theories had predicted. Eastward flights made the clocks lag behind. Westward flights left them slightly ahead. The combination of special and general relativity, so often discussed abstractly, had been weighed and measured in the steady ticking of real devices. To most of us, a few dozen nanoseconds sounds negligible, vanishingly small, too small to matter. But for the physicists comparing the data, it was a triumph. The difference was not random noise or mechanical error. It was precisely what relativity had promised. Even at the modest speeds of commercial airplanes, even at the everyday altitudes of transcontinental travel, time itself had bent. It is comforting to imagine those clocks as travellers in their own right. Packed in foam, cradled in the belly of jets, they ticked steadily as passengers read magazines, sipped coffee, or dozed against windows. From their perspective, nothing unusual was happening, just the regular passage of seconds, one after another. But when compared with their twins at home, their journeys told a deeper story. Each clock carried away a slightly different history of time, like siblings who returned from holiday with diaries that did not match. Experiments like this remind us that relativity is not only about distant galaxies or unreachable black holes, it is about the shape of seconds in the here and now. Haffel and Keating proved that every flight carries with it a quiet distortion of time. Every traveller, whether in business class or economy, returns ever so slightly altered. Their seconds counted differently than the ones who stayed behind. The effect is too small to shape our daily choices, but it is not imaginary. If you were to place atomic clocks on passengers as they boarded and check them again at arrival, you would find that their lives had unfolded at slightly different tempos. What is soothing is the thought that time dilation is not rare or exotic, but continuous. It is not an occasional ripple in the fabric, but a constant property of motion and gravity. The Haffel-Keating clock showed us that relativity accompanies every plane that arcs across the sky, every satellite that orbits Earth, every astronaut who circles above. It is always there, adjusting the seconds, balancing the books of space-time so that the constancy of light is never broken. Imagine, if you will, sitting on a flight yourself, the cabin dimmed, the steady hum of engines like a lullaby. Outside the windows, the curve of the earth stretches below, clouds painted silver by the moon. Inside, the seconds you feel, reading a page, closing your eyes, drifting into sleep, are yours, personal, unremarkable. Yet in those very moments, the fabric of time is bending, quietly stretching or contracting depending on your direction, your altitude, your speed. You're carrying with you a slightly different now than the one waiting on the ground. This experiment is one of the reasons we can say, without hesitation, that relativity is not speculation. It is measurement. It is data. The ticking of clocks has told us that time dilation is real, that Einstein's equations describe the world faithfully, that the universe cares about motion and gravity in ways we cannot ignore, and the beauty lies not only in the numbers, but in the ordinariness of it all. Planes, passengers, and clocks proving cosmic truths while the world below continued its daily routines. So when you hear that relativity was confirmed, you can picture not only distant observatories or massive accelerators, but also jets streaking across the night sky, their cargo hidden, their passengers unaware that they were part of one of the quietest, grandest experiments in history. When you think of laboratories, you may picture chalkboards filled with equations, or quiet rooms where scientists shuffle papers and stare into screens. But some laboratories are more like cathedrals to motion. These are the particle accelerators, vast rings of magnets and tunnels that bend and whip tiny fragments of matter until they move at speeds so close to the speed of light that even the smallest difference becomes meaningful. Within these machines, Einstein's ideas are not abstract at all. They are the very reason the experiments work. Take a particle that lives only a fleeting instant. A pion, for example, has an average lifetime of just 26 billionths of a second. In still air, that is not even enough time for it to cross a single room. Or consider again the muon, cousin to the electron, which in the laboratory survives for just 2 millionths of a second. These are sparks of existence, here and gone almost at once, so fragile they seem unsuited for study. And yet, in accelerators, we can hold them long enough to learn their secrets. How? By giving them speed, by handing them time dilation as a gift. When a particle is boosted to a velocity of 99.9% of the speed of light, its Lorentz factor swells to dozens or even hundreds. That swelling stretches its lifetime in our frame. What would have been 2/millionths of a second at rest becomes dozens or hundreds of times longer. Enough for detectors to record the tracks it leaves behind. Enough for experiments to gather data. Enough for fleeting sparks to linger in the human world. It's as if the universe whispers to these particles, "Hurry, and I will let you stay." Motion bends their time so that they outlast themselves. For the particle, nothing has changed. Its own tiny clock still ticks faithfully, each beat lasting the same as always. In its perspective, it decays when it should. But to us, watching from the lab, its clock has slowed, its moments have stretched, its fuse lengthened into something usable. This is why accelerators are not just machines of energy, but machines of time. Without relativity, the very particles we study would vanish before they reach the detectors. With relativity, they survive long enough to leave trails like comets glowing briefly in the dark. Physicists often speak of accelerators as microscopes turned inside out. Instead of glass lenses magnifying light, they use motion and energy to reveal the tiniest structures of matter. But to make that possible, they rely on the dilation of time. Imagine a snowflake caught in a gust of wind. Without the wind, it melts before reaching your hand. With the wind, it races so quickly that the air itself seems to hold it intact a little longer, letting it land softly on your sleeve. The snowflake has not changed, but its journey has been altered. That is what speed does for particles. Perhaps the most famous of these machines is the Large Hadron Collider near Geneva, a 27-kilometre ring buried beneath fields and villages. Inside it, protons circle thousands of times every second, driven to velocities so extreme that their lifetimes, energies and interactions become playgrounds for relativity. Smaller accelerators around the world perform similar feats, studying muons, mesons, and other unstable fragments of the quantum zoo. In each case, Einstein's equations are not simply acknowledged, they are built into the design. Magnets, detectors, and computing systems are all calibrated to account for the stretched lifetimes of moving particles. If you were to step into one of these facilities, you might hear the low hum of machines, the clicking of detectors, the faint rush of cooling systems. Everything would seem ordinary. But behind the walls, tiny beings of matter are living in dilated time, each second of their existence elongated by motion, each spark glowing longer than nature first intended. It is a reminder that time dilation is not exotic. It is engineered, controlled, used daily by scientists to peer into the heart of reality. There is something almost tender in this. Particles destined to vanish too quickly are given reprieve by motion. We, the observers, benefit from their grace period, but they are not aware of it. To them, nothing unusual has happened. Their private clocks tell the same story they always have. The contradiction dissolves only when we remember that time is not universal, but bound to each path. When you hear of particle discoveries, new bosons glimpsed, rare decays recorded, collisions mapped, it is worth remembering that each result depended not only on high energies, but on time dilation itself. Without it, the universe would keep its secrets locked in lifetimes too short for us to catch. With it, even the most fleeting sparks are stretched just enough to be studied. So, in the quiet of your evening, imagine these particles not as abstractions, but as tiny travellers. Picture them as fireflies in a dark meadow, each glowing for a fraction of a second before winking out. Now imagine giving them speed and watching their glow linger, their trails weaving through the night. That is what an accelerator does. It takes the briefest of lives and lets them shine just a little longer, enough for us to marvel at their existence. Time dilation, once again, proves itself not just a curiosity of thought, but a working principle of our world. It stretches the lives of particles, it steadies the beams in accelerators, it gives science its foothold in the fleeting, and it reminds us gently that the laws of the universe are not barriers but invitations. If you move quickly enough, time itself will make room for you, just as it does for the muons and mesons dancing invisibly beneath our feet. The truth of relativity might feel abstract when we imagine light clocks on trains, or muons tumbling from the sky. It may feel remote when we picture neutron stars and black holes, cosmic places so extreme we cannot visit them. Yet time dilation is not only proven in experiments or written in textbooks. It lives in your pocket. It guides your footsteps on city streets. It directs planes across oceans. It synchronizes bank transactions, and it allows the digital world to function. Every time you glance at a map on your phone or send a message that travels across continents, you are leaning on the very principles Einstein uncovered more than a century ago. At the heart of this is GPS, the global positioning system. It sounds almost magical in its simplicity. A small device in your hand listens to signals from satellites orbiting thousands of kilometers overhead, and from those signals it determines exactly where you are, often within a few meters. The satellites send nothing more than timestamps, the precise moment each signal was emitted. Your phone measures how long it took for those signals to arrive, and from that information it calculates distance. Compare distances from at least 4 satellites, and you can be placed on the map with uncanny accuracy. But this neat trick depends entirely on the assumption that all the clocks involved agree. And as we have already seen, in Einstein's universe, clocks do not always agree. The satellites are racing through orbit at thousands of kilometers per hour, and that motion slows their seconds ever so slightly by the rules of special relativity. At the same time, they are high above Earth's surface, farther from its gravitational pull, where time runs faster by the rules of general relativity. The combination means that each day, the clocks on satellites advance by about 38 microseconds, more than those on the ground. 38 microseconds may seem small, a sliver of a blink, but in GPS, where signals race at the speed of light, it translates to an error of kilometers if left uncorrected. Imagine setting out on a walk to a cafe and finding yourself on the wrong street, or directing an airplane to a runway that no longer matches its coordinates. The system would unravel in days. Engineers anticipated this. They adjusted the satellites before launch, tuning their clocks to tick slightly slower on Earth, so that once in orbit they would align with ground time. Ground stations continue to monitor them, applying corrections constantly. The result is that despite relativity's mischief, the satellites and your phone remain in harmony. The blue dot on your screen hovers near your actual footsteps. Every safe landing of a plane, every ship navigating open seas, every driver following a digital map owes its success to relativity's correction. This reliance extends far beyond navigation. Financial systems demand synchronized time down to millionths of a second to record trades and transactions accurately. Communication networks rely on precise timing to keep data aligned across the globe. Even the internet's backbone, the quiet servers and cables that shuttle information invisibly, requires clocks that agree. Without relativity accounted for, messages would drift out of order, calls would misalign, and the digital world would crumble into confusion. To soften this into an image, think of the world's networks as an orchestra. Each musician must follow the same conductor's beat, or the music dissolves into chaos. Relativity, if left uncorrected, would allow some instruments to drift. A violin playing a note too long, a trumpet entering too soon. The result would be cacophony. But by tuning to Einstein's equations, by adjusting each clock, the orchestra remains harmonious. Your phone, your bank, your navigation app, they all play in time because relativity has been woven into the score. It is striking that something once considered almost philosophical, a theory born in the mind of a young patent clerk in 1905, has become the quiet foundation of the global infrastructure. Einstein did not set out to guide commuters or synchronize digital markets. He asked only what would happen if the speed of light were the same for everyone, yet from that question flowed a cascade of consequences that now shape your daily life. There is something calming in this realization. You, sitting quietly tonight, are part of a vast invisible choreography. Satellites circle above, their clocks nudged by relativity. Ground stations listen, adjusting for drifts. Your phone receives signals, triangulating your position. All of it happens without you noticing, as naturally as breathing, and yet beneath it lies the bending of space-time, the dilation of seconds, the most profound reimagining of time humans have ever attempted. So the next time you watch the little blue dot move along a map, imagine the unseen effort behind it. Imagine satellites racing, their clocks sped by altitude and slowed by motion. Imagine ground computers correcting for the tug of Earth's gravity. Imagine your phone quietly calculating, turning those whispers into directions. It is not magic, but it is close. It is physics, unfolding in real time, guiding you home. Relativity is no longer just a theory. It is a tool in your pocket, an ally in your daily tasks. It proves itself not in equations on chalkboards, but in the fact that you arrive at the right cafe, the right corner, the right home. Einstein's insights, once radical, now serve quietly, invisibly, faithfully, and that perhaps is the most remarkable proof of all. If your phone carries the daily imprint of relativity, then so do you whenever you move through the air. The bending of time is not confined to satellites and servers. It touches the seconds you live when you fly across oceans, when astronauts circle Earth, and when rockets leap into space. The effects are tiny for us, but they are real, etched into the very rhythm of our bodies, written into the diaries of our cells. Consider a passenger boarding a long-haul flight. The cabin settles, the engines hum, and the plane lifts from the runway into the sky. For hours it arcs across the globe, a tin can of breathing, reading, dozing humans carried thousands of kilometres in the air. During that journey, the passengers are aging slightly differently than the loved ones waiting on the ground. Their watches tick imperceptibly slower, their seconds stretched by the combined effects of altitude and speed. At cruising height, farther from Earth's gravity, time flows faster. At hundreds of kilometres per hour, speed slows the clocks down. The balance of these effects yields a tiny difference, measurable not with wristwatches, but with atomic clocks. By the time they land, the travellers have experienced a subtly altered passage of time compared with those who never left the ground. This was not speculation, but experiment. In the 1970s, physicists carried cesium beam atomic clocks aboard commercial jets, circling the globe eastward and westward. When compared with reference clocks back at the observatory, the airborne clocks disagreed, not by chance, but precisely as Einstein had predicted. Eastward flights lost nanoseconds, westward flights gained them. The story was not theoretical, it was inscribed in the ticking of real devices. Passengers of those flights became, unknowingly, participants in one of the quietest confirmations of relativity ever performed. The differences may sound trivial, mere billionths of a second, yet they remind us that even at our modest speeds, relativity shadows us, altering the tempo of our lives. For astronauts, the differences grow more noticeable, though still far from science fiction's dramatic leaps. On the International Space Station, orbiting Earth once every 90 minutes, astronauts move at more than 27,000 kilometers per hour. In that high-speed environment, special relativity slows their time compared with ours on the ground. At the same time, their altitude raises them above much of Earth's gravity, where general relativity speeds their clocks. The balance tips so that, overall, their seconds run just a little faster. Across months in orbit, the difference accumulates into a fraction of a second. When they return, they are ever so slightly younger than their earthbound twins. It is a strange thought, to spend months in space, to see continents sweep beneath you, to float with Earth always out the window, and to return carrying not only new memories, but also a body that has lived by a slightly different clock. Your pulse, your dreams, your laughter, all etched into a timeline that does not perfectly match the one at home. This idea was tested most famously with the so-called twin experiment of astronauts Scott and Mark Kelly. Scott spent nearly a year aboard the ISS while Mark remained on Earth. When Scott returned, their biological clocks had diverged, not only due to relativity but also because of the stress of spaceflight. Yet hidden in the comparison was the same truth. Time had not flowed identically for the two brothers. Even our own bodies become experiments when carried into the sky. Rocket travel amplifies the lesson further. As spacecraft reach higher speeds and greater altitudes, the competing effects of velocity and gravity weave more complex patterns into time. For the brief suborbital flights now undertaken by private companies, the difference remains tiny, smaller than the blink of an eye. But one day, when rockets carry humans across the solar system at sustained high velocities, the stretching of time will become tangible. A crew could travel to Jupiter and back, returning not just with tales of storms and moons, but with clocks that no longer matched Earth's by minutes or hours. What is calming in all this is the realization that relativity is not something that disrupts our lives, but something that harmonizes them. The equations that describe how fast or slow time flows for travellers also ensure that cause and effect remain intact, that light remains constant, that the universe does not dissolve into contradictions. Your passport stamps, your airplane tickets, your astronaut missions, all are written on threads of time that bend slightly, yet bend predictably, reliably. If you close your eyes and imagine a traveller in motion, you might see them walking with a lantern in hand. The lantern glows steadily, marking their seconds, unchanging from their perspective. But as they climb higher into the air or accelerate faster across the sky, the glow shifts in relation to the lanterns left on the ground. From afar their light seems slower or quicker, but to them it always shines the same. Relativity is the story of how those lanterns remain faithful, even when their rhythms diverge. For you, this means that the next time you look up at a plane streaking white across the blue, you can whisper to yourself, "Everyone on board is living just a little differently than I am." Their seconds are stretched, their minutes tuned by altitude and motion. They will step off the plane carrying a personal slice of time that does not perfectly overlap with yours. And though you will never notice, the difference is there, real and quiet. A passport stamp written not on paper, but on the fabric of space-time itself. We have followed relativity through airplanes and rockets, through satellites and astronauts, but its reach does not stop at the edge of spaceflight. It threads itself into more familiar and practical corners of life, into hospitals where radiation therapy is planned, into laboratories where beams of particles are tamed, into electronic systems that depend on synchronized time. Even where we do not expect it, time dilation hums quietly, shaping outcomes and designs, ensuring that the modern world functions as smoothly as it does. Let us begin in a place that feels far from physics, the hospital. Here, in quiet, bright rooms lined with machines, patients sit or lie down while doctors prepare treatments that must reach the cellular level. In radiation therapy, beams of particles, sometimes electrons, sometimes protons, are directed with precision toward cancerous tissues. These beams are accelerated to high speed so they can penetrate deeply into the body, reaching tumours that would otherwise be shielded by bone or muscle. At those speeds, relativity asserts itself. The particles live longer, travel straighter, and behave differently than they would at rest. Engineers who design these machines must account for time dilation, because it shapes the range and behaviour of the beams. What began as a theory about trains and clocks has become a safeguard in medical care, extending lives by bending time in the service of healing. Beyond hospitals, accelerators themselves, smaller than the famous ones that hunt for new particles, are used in industry and medicine. They sterilize food, create isotopes for imaging, and test materials for resilience. In every case, their designers know that high-speed particles do not obey the old Newtonian rules. Their lifetimes stretch, their paths lengthen, their decay slows, all thanks to relativity. Without that, the machines would miss their marks, beams would dissipate too quickly, and the quiet reliability of these tools would fail. Even in the world of electronics, relativity has a voice. Modern systems depend on precise synchronization. Computers in data centers, stock markets where trades occur in millionths of a second, communication networks that stitch continents together. A difference of microseconds in one part of the world can mean errors, mismatched transactions, or failures in coordination. Engineers rely on time standards anchored in atomic clocks, corrected for relativity, so that the pulses guiding electronics remain in harmony. Without those corrections, the digital world would unravel into noise. One way to picture this is as a conversation at a crowded table. Each person must wait their turn, speak in order, listen carefully. If one voice drifts even slightly, the conversation becomes confusion, with overlaps and silences in the wrong places. Relativity, if ignored, would let those voices slip out of sync. By correcting for it, we ensure the conversation continues smoothly, the meaning intact. Relativity also slips into technologies less visible, but still important. Satellite communications, geological surveying, weather forecasting, and even the operation of some scientific instruments that monitor Earth's crust or atmosphere. Anywhere signals travel at light speed and distances or altitudes differ, relativity hums beneath the surface. The corrections are often automatic, invisible to users, but they are there, steadying the flow of information. If this all sounds technical, imagine instead a simpler image. Think of the world as a vast, intricate clock. Each city, each machine, each person is a gear in that clock, turning at its own pace. For the clock to function, the gears must mesh smoothly. If one gear speeds up or slows down even a little, the whole system falters. Relativity ensures that we know precisely how each gear behaves, depending on its motion and its place in the gravitational landscape. It does not remove the differences, it explains them, lets us account for them, and keeps the whole clock turning together. This is perhaps the most reassuring part of Einstein's vision. Time dilation is not a nuisance, not a glitch to be feared. It is a law that gives us predictability. Engineers, pilots, doctors, scientists, they can all design around it because it is consistent. The stretching of seconds may feel counterintuitive, but it is steady, measurable, and dependable. That steadiness is what allows satellites to guide you to a cafe, accelerators to treat disease, and financial systems to record the exact sequence of trades. So while we often think of relativity as lofty or difficult, it is woven into the ordinary. It is in the signals that cross the air between your phone and a satellite. It is in the quiet hum of a hospital machine focusing beams on a hidden tumour. It is in the blinking lights of servers that carry your words to someone far away. It is the invisible conductor, ensuring that the orchestra of modern technology does not fall apart. Next time you tap your screen to check a map, or hear of a medical breakthrough, or read about the precision of electronic trading, pause for a moment. Beneath all of it lies a truth discovered by asking what would happen if light were the same for everyone. That simple question reshaped physics and now guides the everyday fabric of our world. And perhaps, in reflecting on this, you might feel a gentle comfort. Time dilation is not only a reminder of the strangeness of the cosmos, but also of its generosity. It gives us tools, stability, and harmony. It bends in ways that do not break us but support us. Einstein's equations are not abstract riddles left in dusty books. They are guardians at work in your daily life, helping your world stay stitched together. There are places in the universe where time itself seems to hesitate, where the seconds falter and stretch until they nearly stop. These are the regions around black holes, the collapsed remnants of stars so heavy that their gravity does not merely bend space-time, it folds it into an abyss. In earlier sessions, we pictured valleys of time and rivers flowing more slowly in deeper channels. A black hole is the ultimate valley, the deepest of channels, a place where the flow of time itself grows thick and hesitant, where outside observers and falling travellers tell stories so different they might seem contradictory, yet both remain true. Imagine watching a star collapse. At first, it is only a faint glow, shrinking as fuel runs out and nuclear fire wanes. Then gravity takes over, pulling everything inward. At a certain point, the collapse passes a threshold. The matter compresses beyond rescue, forming a region so dense that escape becomes impossible. The edge of this region we call the event horizon. To cross it is to vanish from the outside world, to enter a realm where light itself cannot return. Now imagine standing at a safe distance with a powerful telescope, watching an object fall toward that horizon. Perhaps it is a spacecraft, or even something as ordinary as a rock tumbling inward. From your perspective, something strange occurs. As the object nears the horizon, its motion appears to slow. Each signal it sends, flashes of light, radio pings, arrives more and more delayed, stretched into longer wavelengths. The bright surface reddens, dims and fades. Time for that object, from your vantage, seems to grind almost to a halt. You never see it cross the horizon. It lingers there indefinitely, frozen in a kind of eternal twilight. But here is the paradoxical beauty. If you could ride with that falling object, if you were the traveller instead of the observer, you would feel nothing unusual. The seconds on your watch would tick as they always do. Your heartbeat would keep its rhythm, your thoughts would flow one after another. You would cross the horizon without drama, without any sense of slowing. To you, time is faithful, unbroken. To the outside world, your clock has nearly stopped. Two voices telling the same story, each true within its frame, each shaped by the bending of space-time. This is what makes black holes feel like riddles whispered by the cosmos. They force us to accept that reality is not single-threaded, but layered. One perspective sees a freeze, another sees a fall. Neither is wrong. Both are stitched into the fabric of relativity. To soften the idea, think of a story told around a campfire. One person recounts it, slowly, drawing out each moment, pausing on every detail. Another rushes through it, reaching the end quickly. Both are telling the same tale, but the tempo differs. A black hole is like that campfire story, except the difference in tempo is written not by choice, but by gravity itself. For astronomers, these differences are not just curiosities, but clues. Light escaping from near the horizon arrives stretched into redder hues, a signal of gravitational redshift. Timing of matter swirling into the hole, X-rays flickering from hot gas, even the way gravitational waves ripple outward from merging holes, all carry the imprint of time being distorted. Instruments on Earth and in orbit have measured these effects, confirming again and again that Einstein's predictions hold even at the brink of infinity. Yet despite their extremity, black holes also feel strangely familiar. The same equations that stretch seconds in satellites, that lengthen muon lifetimes, that demand corrections in GPS, are the ones that predict this freezing and falling at horizons. The law is universal, from your phone to the edge of a star. Black holes are simply the loudest expression of the same quiet principle. Perhaps it is comforting, too, to remember that for the traveller time never falters. Your seconds are always yours. You never feel them stretch or shrink. You live them as they arrive. Even falling into the darkest abyss, you carry your private now faithfully, unaware that others see it as nearly stopped. That contrast is less frightening than it is humbling, a reminder that time is intimate, stitched to the path you take, indifferent to what others may measure. If you want a gentler metaphor, Think of standing by a window during a heavy snowfall. A friend walks into the distance, flakes swirling around them. From your perspective, their steps seem slower and slower as the storm thickens, until eventually you can hardly tell if they are moving at all. But to your friend, each step feels the same as the last. They are still walking, still breathing, still thinking, unaware that the storm has blurred them into stillness from your view. The black hole is that storm, space-time itself thickening until outside witnesses see motion nearly halt, while the traveller continues unbothered. So black holes, far from being only destructive monsters, are also teachers. They show us the limits of relativity in the most dramatic classroom. They remind us that truth can look different depending on where you stand, and that reality can hold two versions of the same story without contradiction. And when you close your eyes tonight, you might imagine yourself as both the observer and the traveller. One part of you stands at a distance, watching time stretch into stillness, seeing signals redden and fade. Another part falls calmly inward, your seconds steady, your heartbeat unchanged, your journey continuing naturally. Two voices, one fabric, one story told in different tempos. That is the edge of infinity, the place where time bends into paradox yet remains, somehow, a lullaby whispered by the universe itself. Black holes may be the most dramatic storytellers of time, but just before a star collapses into that final abyss, there is another possibility. If the mass is great but not overwhelming, the collapse halts at a different threshold, producing an object so dense that it is almost beyond imagination, yet not quite beyond our reach. These are neutron stars, the stellar remnants that sit on the brink of infinity, not fully gone into darkness but compressed into a form where the weight of entire suns is crushed into a sphere barely wider than a city. Imagine taking the mass of our sun, a body that could hold more than 1,000,000 Earths, and pressing it into a ball only 20 kilometers across. What was once a luminous globe becomes a sphere of neutrons packed shoulder to shoulder, a solid so dense that a teaspoon of its matter would outweigh mountains. This is a neutron star, a stellar ember still glowing with energy, still pulsing with magnetism, still bending space-time with a force that slows time significantly compared with distant space. On the surface of such a star, gravity is more than 200 billion times stronger than on Earth. Clocks placed there would tick far more slowly than ours. If you could stand on that surface, which of course nobody could withstand, your seconds would feel normal to you. Your heart would beat, your breaths would follow one after another, and you would never notice anything unusual. Yet to a distant observer, every one of your signals, your voice, your light, your heartbeat measured remotely, would arrive stretched out, slowed, shifted into redder tones. Time for you would be syrupy compared with time for them. Astronomers glimpse this not by sending people to neutron stars, but by listening to their emissions. Many neutron stars are pulsars, spinning rapidly, sweeping beams of radiation like cosmic lighthouses. Each spin is regular, like the ticking of a giant stellar clock. But those ticks are not quite what they would be if measured in the absence of gravity. The star's immense pull dilates its own time, slowing its signal. We can see this in the redshift of X-rays and in the steady delay of pulses, both of which carry the fingerprint of time running thick on the star's surface. It is striking to think that somewhere in the galaxy, stars are ticking away like immense hearts, their beats slowed by gravity itself. These are not metaphors alone. Astronomers truly call them stellar clocks, because their rhythm is so precise that they rival the atomic clocks we use on Earth. Some pulsars rotate hundreds of times per second, and yet their pulses arrive with the steadiness of a metronome. Each tick is a reminder that time's pace can be measured even in such extreme environments. And here relativity does more than predict, it explains. Without the slowing of time, On the neutron star's surface, the signals we measure would not match the frequencies we detect. The shift toward lower energies, the gravitational redshift, would be absent. But it is there, painted in the spectra, proving that Einstein's geometry holds true even under crushing gravity. To soften the image, imagine standing at the edge of a great waterfall. The river above flows quickly and smoothly, but as it nears the drop, it pools and swirls, slowing into thick eddies before tumbling over. Neutron stars are that brink, where time does not halt completely, as at a black hole's horizon, but slows into deep swirls, heavy and patient. Their light is like water flowing from that pool, stretched and reddened before it rushes away. Neutron stars also remind us of continuity. They are born in supernova explosions, the deaths of massive stars, yet they continue to exist as markers in the galaxy, ticking steadily for millions of years. They are like scar tissue in the cosmos, remnants of past violence that now serve as clocks and beacons, and the very slowing of their time is part of what lets them be so steady. Their internal rhythms, though extreme, are predictable. Astronomers use them as cosmic yardsticks, as anchors in maps of the galaxy, as laboratories for testing relativity itself. There is a poetic comfort in knowing that while some stars collapse completely into black holes, others remain on the edge, holding their shape, their voices still reaching us. They are stars that should by rights be gone, yet they linger, their seconds stretched by gravity, their signals slowed but not silenced. They stand as monuments to the elasticity of time, proof that even in the face of collapse something can endure. So when you read of pulsars or see artists' impressions of neutron stars with their beams sweeping the darkness, picture them as hearts beating in slow motion. Imagine their seconds dripping heavily, their light struggling uphill against gravity, their clocks lagging compared to ours. And imagine too that somewhere across the galaxy there are thousands of these hearts ticking away, filling the cosmos with a rhythm we can detect from Earth. Black holes teach us that time can nearly stop. Neutron stars teach us that time can slow to a crawl, yet still beat with remarkable precision. Together they form a kind of duet, one silent, one pulsing, both telling us that gravity is not merely weight, but also tempo. Your seconds on Earth flow faster than they would on those stars, but the principle is the same. We all live in the valleys carved by mass, carrying clocks tuned to our surroundings, ticking faithfully whether quick or slow. If neutron stars are the ticking hearts of the cosmos, then black holes colliding are the drums, and the universe itself is the instrument through which their sound travels. That sound is not audible in air, because there is no air in space. Instead, it is the trembling of space-time itself, ripples spreading outward from the most violent events the cosmos can stage. These ripples are what we call gravitational waves, and they are another reminder that time is not rigid but flexible, not silent but resonant, able to be shaken and stirred like the surface of a pond. The idea of such waves was written into Einstein's equations in 1916. If gravity is the curvature of space-time, then moving masses, especially those accelerating violently, should send disturbances outward. Just as a pebble tossed into water creates circular ripples, a pair of orbiting stars should create ripples in space-time. For decades, these waves seemed theoretical, too faint to detect, vanishing into the vastness. Yet the prediction lingered, waiting for instruments sensitive enough to hear the faintest tremor. Picture two black holes locked in a spiral dance, each many times the mass of our sun. They circle closer and closer, their orbit tightening, their speed accelerating until they are moving at a significant fraction of light's pace. With every orbit they disturb space-time, sending waves outward in all directions. As the dance reaches its climax, they merge into a single black hole, and in that final instant the largest waves are launched, racing across the universe at light speed. Billions of years later, Some of those waves pass through Earth, stretching and squeezing our world by amounts smaller than a fraction of a proton. They are unimaginably faint, yet they are there. To detect them, scientists built LIGO, the Laser Interferometer Gravitational Wave Observatory. Two enormous L-shaped detectors, one in Louisiana and one in Washington, use laser beams stretched across kilometers of vacuum tunnels to measure the tiniest changes in distance. When a gravitational wave passes, one arm lengthens while the other shortens, then they swap. The change is so small it defies intuition, but the lasers interfering like ripples in a pond reveal the tremor. In 2015, LIGO recorded its first signal, the collision of two black holes more than 1 billion light-years away. The universe itself had rung like a bell, and at last we heard it. The metaphor of bells is not an exaggeration. Scientists often convert the data from these detections into audio, compressing the signals into frequencies we can hear. The result is a brief chirp, a rising tone that ends suddenly as the merger completes. To know that the sound you're hearing is not air vibrating, but space-time itself, trembling, is profoundly moving. It is as if the cosmos had struck a chord and we were finally quiet enough to listen. Gravitational waves are not only confirmations of Einstein's theory, though they are that too. They're also messengers, carrying information about things otherwise invisible. Black holes, by definition, emit no light. But when they collide, their waves spread outward, and those waves tell us their masses, their spins, their distance. With each detection, we learn more about the hidden population of black holes, neutron stars, and even the history of the universe. Time itself becomes a messenger, delivering news from places where no telescope can see. To soften this into an image, imagine the universe as a vast ocean at night. The stars above are reflections on the surface, the galaxies are the waves and currents, but deep beneath, two whales collide in a dance, their energy sending ripples outward. Far away, a boat feels a gentle rocking on its hull. That rocking tells the sailors, without ever seeing the whales, that something vast has moved in the darkness. Gravitational waves are that rocking, a tremor in the ocean of space-time. What is perhaps most soothing is that even as the universe produces unimaginable violence, collapsing stars, colliding black holes, neutron stars cracking like glass, the waves that reach us are faint, gentle, harmless. They stretch and compress Earth by less than a proton's width, a motion utterly beyond sensation. You are living in a world that trembles constantly, and yet you feel nothing. The cosmic bells ring, and their notes arrive as whispers. And yet those whispers confirm that time is not just a background flow, but something that can be stirred. When a gravitational wave passes through you, your seconds lengthen and shorten minutely. Your very sense of duration is shifted, even if you cannot tell. Time, which feels so solid, so trustworthy, quivers like a string under tension. And the universe, in its patience, allows us to notice. As you lie here tonight, you might imagine the entire cosmos as a great cathedral, black holes and neutron stars serving as organ pipes, galaxies as the walls, and space-time itself as the air inside. Every so often, when massive objects collide, a note is played, resonating across billions of light-years. LIGO is the ear pressed to the stone, listening to the faint vibration, and we, in turn, are the congregation, finally aware of the music that has always been playing. Gravitational waves close the circle of our story so far. They confirm the bending of time predicted by relativity. They reveal the extremities of neutron stars and black holes, and they remind us that the universe is not silent. It is alive with rhythm. And though those rhythms are far too subtle to disturb your evening, the knowledge of them may settle over you like a lullaby, the awareness that the fabric beneath you is not still but softly singing. carrying the memory of cosmic dances through every second you live. Up to this point, we have seen time bend under speed, slow in the grip of gravity, stretch in particle beams, and nearly stop at the edges of black holes. These are dramatic images, suitable for cosmic scales and experimental halls. But relativity is not only about extremes, it is also about something more subtle, a change in perspective so gentle that it feels philosophical as much as physical. It is the idea that even the notion of now is not universal but personal, woven into the fabric of each observer's journey. This is the relativity of simultaneity. To feel its strangeness, imagine you are standing by a railway track at night. A train rushes past, long and sleek, carrying passengers seated under lamps. At the exact moment the middle of the train passes you, lightning strikes both ends of the train. From your vantage point on the ground, you see both flashes at once. The thunder rumbles later, but the light reaches you simultaneously. You declare, confidently, that the bolt struck at the same time. That is your now. But for a passenger seated at the very centre of the train, things are different. As the flashes occur, they speed forward toward the front and backward toward the rear. Yet the train itself is moving forward. This means the passenger is rushing toward the flash from the front and away from the flash from the rear. Light travels at the same speed regardless of motion, so the flash from the front reaches the passenger sooner than the flash from the rear. From inside the train, it seems that the front bolt struck before the rear one. Their now is not yours. Who is correct? In Newton's world, there would be only one answer. Simultaneity would be absolute, shared by all. But Einstein's world is more nuanced. Both observers are correct within their own frames. What counts as simultaneous depends on motion. The concept of a universal now, stretching across the cosmos like a single blanket, dissolves. Instead, every observer carries their own slice of the present, cut differently depending on their movement through space-time. The image can feel unsettling, as though the shared world we trust is fractured. If I say two events happened at once, and you insist they did not, how can both of us be right? The answer lies in the constancy of light. Because light refuses to adjust its speed for anyone, space and time must do the adjusting. And one of the things they adjust is our judgment of simultaneity. To soften this idea, picture a stage play performed in a round theatre. Audience members seated on different sides of the circle see the actors at slightly different moments. A gesture that looks simultaneous from one angle looks staggered from another. No seat is privileged. Each view is valid. The play unfolds as one story, yet each perspective slices it differently. Time is like that stage. Your seat, your motion, determines how you perceive the order of events. For daily life, the differences are negligible. Two friends watching a football match on opposite sides of the field will never disagree about whether a goal was scored before the whistle blew. But at cosmic scales, or with motions near light speed, the differences grow undeniable. The relativity of simultaneity is not just a curiosity, it is the foundation for why time dilation exists at all. If now is relative, then different observers can measure different durations, and both can be right. This realization touches something deeper than physics. Our private sense of the present, of being here together in this moment, feels absolute. Yet physics tells us it is not universal. Your now may not be mine. Across the galaxy, an alien civilization might count as simultaneous events we would judge as separated by centuries. Their present is not ours, though both unfold within the same universe. Perhaps this thought can be soothing rather than troubling. It suggests that the present moment is intimate, a personal possession, carried with you like a candle through the dark. There is no cosmic referee declaring whose now is correct. There are only countless private nows, stitched together into the fabric of space-time. So next time you sit quietly, perhaps listening to rain against a window or a kettle, beginning to murmur on the stove, pause to remember that your present is yours alone. Someone speeding in a satellite, someone standing on a distant mountain, someone orbiting another star would slice the universe differently. Their sense of now would not match yours, and yet each would be faithful to the same rules. The train, the flashes of lightning, the moving passenger and the stationary observer all are right. The relativity of simultaneity reminds us that time is not a single flowing river carrying everyone downstream at once. It is more like a branching delta, where each traveller floats down their own channel, some winding, some straight, some converging for a while, and then diverging again. Where you declare, this is now, someone else will declare, that was earlier, or that will be later. And the fabric of space-time accepts both without contradiction. This quiet realization prepares us for even deeper reflections, that cause and effect themselves are bounded by light, that the shape of possibility is carved by cones of influence, and that the universe may be less a flowing story and more a sculpture containing all events at once. But before we step into those philosophies, it is enough to hold gently this thought. Your present moment is real, but not universal. It is a candle you carry, casting a glow around you, one that overlaps with others sometimes but not always. And in that gentle glow lies the intimacy of being alive, moving, breathing, and belonging to a particular slice of the cosmos. If the relativity of simultaneity shows us that now is not shared universally, then light cones show us the quiet rules that decide which events in the universe can touch each other at all. They are not cones of metal or stone, but cones traced in the geometry of space-time itself, delicate boundaries that separate what can influence what and what must remain forever apart. Imagine striking a match in a dark room. The flame flares, and light radiates outward in every direction. If you were to mark every possible path that light could take from that flame, you would trace a cone, expanding wider as moments pass, reaching farther into the future. This is the future light cone of that spark. Everything inside it is reachable. Everything outside it will never know the match was struck. The cone is the map of influence, the region of space-time touched by that small flare. The same picture works backward. If you are here, now, sitting quietly listening, everything that could have affected you, every photon, every sound wave, every gravitational tug that had time to reach you, lies inside your past light cone. A star that exploded 1 billion years ago and sent its light across space sits in your past cone, its photons now reaching your eyes as starlight. A car horn outside your window from a minute ago sits in it too, its sound now in your ears. But events outside your past cone, things too far or too recent, cannot have touched you yet. They remain strangers. Together these cones, past and future, give shape to your personal universe. They form the lantern of causality you carry with you, illuminating what can affect you and what you can affect. They remind us that physics does not allow all events to be tangled freely. There is order, there are boundaries, there is structure hidden beneath the flow. One of the subtler consequences is that outside these cones, order itself can shift. Events that one observer insists came in a certain order may appear reversed to another. Was lightning strike A before lightning strike B? If both strikes are outside each other's cones, then different observers in motion can disagree, and neither is wrong. The universe allows flexibility outside the cones, but not within them. Inside, cause and effect remain absolute. A cup falls, then shatters, a switch is flipped, then a light turns on. Those relationships never break. It is only at the edges beyond influence that the order can shuffle. To soften this into something gentler, imagine standing in a theatre, the stage before you lit by a circle of lamps. The actors you see moving within that circle are the ones who can reach you, their gestures visible. Beyond the light in the dark corners, actors might move, but their motions do not touch you. The light cone is like that circle of illumination. It defines the possible connections, leaving the rest in silence and shadow. Physicists draw these cones on diagrams, time running vertically, space running horizontally. The cones stretch upward and downward, their sides slanted at the angle of a light speed. But you do not need the diagrams to feel their meaning. All you need is the awareness that your life is carried inside one of these cones at every instant. Your choices ripple outward only so far, reaching those who lie within your future cone. Your experiences are shaped by what arrives from your past cone. Everything else, no matter how intriguing, remains unreachable. What is soothing is that this picture restores a sense of order to relativity. Yes, simultaneity is relative, yes. Different observers carve different nows. But light cones give everyone the same boundaries for cause and effect. No observer can make the cup shatter before it falls. No perspective can let information travel faster than light. Within the cones, the story is consistent for all, and beyond physics, the imagery can be calming in its own right. To think of yourself as carrying a lantern of causality through the dark is strangely reassuring. The cone lights your path into the future. It gathers your influences from the past, and it keeps the universe coherent. You may never see the cones themselves, but they're always there, silently shaping what you can know and what you can change. Perhaps tonight, as you sit listening, you can picture your own light cone expanding gently upward into the future. It includes the message you might send to a friend tomorrow, the footsteps you might take across a street, the words you might whisper before sleep. And behind you, in your past cone, are the stars whose photons are still travelling, the breaths you have taken, the memories stitched into your life. The rest of the universe lies outside, unreachable yet still existing, waiting in shadows your light can never cross. So light cones are more than technical diagrams. They are the poetry of possibility. They tell us not only what time is, but what time allows. They remind us that every moment is both a limit and a gift. You cannot affect everything. You cannot know everything. But within your cone you can live fully, faithfully, carrying your own now into the future. We have seen how motion stretches seconds, how gravity thickens the flow of minutes, how light cones limit what can touch us, and how simultaneity itself is not the same for everyone. All of these pieces point toward a picture of the universe that is perhaps the most serene and most unsettling of all, that time does not flow at all. Instead, it simply is, existing as a vast four-dimensional sculpture. This is the block universe, a vision in which past, present and future all coexist like carved patterns on an unchanging stone. The metaphor of a river has guided us often, time flowing steadily, carrying us from past through present into future. It is how our minds naturally feel time, always moving, always slipping away. But relativity invites another image. Imagine not a river, but a frozen glacier. Its ridges, valleys, and crevasses are all there at once. Where you stand is a single point on its surface, but every other point exists just as surely whether you're there or not. In the block universe, your birth is a carved notch, your future footsteps already etched, your every moment fixed in the structure. You experience them sequentially because of how your consciousness moves, but the structure itself is timeless. Relativity almost demands this view. If different observers slice space-time into different nows, then there can be no single, universal present. What feels like the present to you might be someone else's future or past. All events must therefore exist equally, otherwise the disagreement could not be reconciled. The block universe is not an invention of philosophy alone. It is one way of making sense of the relativity of simultaneity. This does not mean free will is a mirage or that life is predetermined in the sense of a script you must act out unwillingly. Instead, it invites a gentler reflection that all moments of your life are already woven into the tapestry, but you, as a conscious being, trace them one at a time, like a finger running slowly across a painting. You cannot see the whole canvas at once, but that does not mean it is not there. To soften this, imagine walking along a frozen river at twilight. Beneath the ice are swirls and eddies, captured in place, motionless yet intricate. You move step by step, feeling as though the river flows beneath you, yet it does not. It is you who move, not the ice. Consciousness gives you the sensation of flow, even when the structure is still. Physicists who describe this picture sometimes call space-time a block, because it is fixed, but the image need not be harsh. You might think of it as a vast library, every book already written, each page already bound, yet each reader moving at their own pace. From the standpoint of the library, all stories exist simultaneously. From the standpoint of the reader, the story unfolds word by word. You are both the reader and the character, immersed in one perspective of time while existing fully in another. For many listeners, the block universe can feel cold at first, like a denial of the warm flow of moments. But it can also feel comforting. If every event exists equally, then nothing is truly lost. The laughter of your childhood, the embrace of a loved one long gone, the moments you fear slipping away, they are still there, carved into the sculpture. You cannot return to them in practice, but they are not erased. They remain part of the eternal fabric. There is poetry in thinking of yourself as a path through this sculpture. Your path has bends, accelerations, still points, valleys where gravity slowed you, and moments where velocity stretched your seconds. Yet all of them are etched together into one unbroken thread. Others have their own threads, weaving alongside yours, sometimes close, sometimes far, sometimes intersecting. The sculpture is not just yours, but everyone's, and the great cosmos beyond. The block universe also speaks to the quiet question of death. If all moments exist, then endings are not annihilations, but boundaries, like the final page of a novel that still remains in the book even after you close it. The story remains part of the whole. The flow you feel ceases, but the pattern is there, permanent. It is a thought that has given solace to some physicists and philosophers, the idea that existence is never truly lost, only completed. From a scientific perspective, this picture is not the only interpretation of relativity, but it is one of the most natural. From a human perspective, it invites us to slow down, to see our present not as a fleeting slice slipping away, but as a facet of something larger, timeless, serene. Tonight as you listen, you might imagine your life not as a stream slipping away, but as a sculpture already complete. Each moment is a glint in that sculpture, polished by your awareness as you pass it. You need not hurry because nothing is truly vanishing. Every second you live is inscribed. Every choice you make is etched, and your consciousness is the quiet reader, turning one page at a time. Perhaps this vision is not frightening but calming. You're not racing down a river, desperate not to lose the seconds. You're walking gently through a gallery where every painting already hangs, every moment already exists. Your task is simply to notice, to feel, to experience your private now, knowing it will never be erased. We have walked together through trains and satellites, through particles and pulsars, through valleys of gravity and the edges of black holes. We have heard the universe sing with gravitational waves, and we have imagined our lives etched into a sculpture of space-time. Now, as our journey comes to a close, it is time to gather these threads and bring them back to where they began, to you sitting quietly living through your private seconds. Among the most haunting implications of time dilation is its promise for travel among the stars. Imagine a crew of explorers boarding a ship capable of approaching the speed of light, To them, the journey to a distant star system might take only a handful of years. Their clocks would tick normally, their meals would come each day, their friendships would unfold in steady rhythms. But back on Earth, decades or even centuries might pass. Children not yet born at their departure would be grandparents at their return. Nations might change, languages evolve, cities rise and fall, all while the travellers felt only a short absence. This possibility is not science fiction, but a quiet consequence of relativity. Proper time, the time measured along one's own path, differs depending on speed and gravity. For the travellers, their proper time is the only reality. They will not feel robbed or stretched. Yet when they return, they would find the world aged beyond recognition. Time dilation makes the stars reachable in one lifetime, but only by severing continuity with home. It is a gift and a loss wrapped together. On a larger scale, time dilation also shapes how we see the universe's past. The light that reaches us from galaxies billions of light years away has been stretched by the expansion of space itself. Its colours shifted redder, its flickers slowed. We peer into the cosmic microwave background, the faint afterglow of the Big Bang, and what we see is not just distance but dilation. The universe itself has aged, its rhythms are stretched as it expanded. To study cosmology is to study time's elasticity written across the heavens. Even gravitational waves, those faint ripples we spoke of, are messages about time. When black holes collide, they do not merely curve space. They shake time itself, sending pulses of stretched and compressed seconds through the cosmos. To detect them is to hear the heartbeat of the universe across unimaginable distances, proof that time is not fixed but trembling, alive. And then there is the personal scale, the one closest to your quiet breath as you listen now. Relativity teaches us that there is no universal present, no single now shared by all. Each of us carries our own private moment, stitched to our own motion, our own position in space-time. Your now is yours, my now is mine, an astronaut's now is theirs. It is not a flaw but a feature of the universe, the intimacy of time given to each traveller. There is a kind of solace in this. The present moment feels so fragile, like sand slipping through your hands, yet relativity assures us that every moment is etched forever into the fabric. Your laughter of years past, your quiet choices of today, the memories you will make tomorrow, they all exist, not flowing away but stitched into the sculpture. The flow you feel is consciousness reading the pages, but the pages remain. As we come to the end of this exploration, it may help to return to the simplest images we carried at the start. A clock on a train, ticking slower than one on the platform. A valley of time where seconds pull thick like syrup. A satellite's clock corrected so your phone can find your home. Each image is small, yet each reveals the same truth. Time bends. It stretches for travellers. It slows near gravity. It dances to keep light constant. It ripples when stars collide. Time is not rigid but responsive, intimate, alive. And what does this mean for us, who live not in equations but in feelings, in memories, in breath? Perhaps it means we can hold our seconds more gently. If time is personal, then your now is enough. You need not measure it against the clocks of others. If time is elastic, then each moment is precious, not because it slips away, but because it is uniquely yours, woven into your path. And if the universe holds all events together like a sculpture, then nothing is truly lost. All that you have lived remains, carved into space-time's patient fabric. So tonight, as you prepare for rest, let these thoughts settle like quiet dust. You are part of a cosmos where time dilates and bends, where simultaneity dissolves, where private nows coexist. You're part of a story vast beyond telling, yet tender enough to hold your heartbeat. And though the stars may spin and galaxies drift and black holes pull, your seconds are yours, faithful and unrepeatable, and so we close. Thank you for sharing this gentle journey, for listening through trains and clocks, through particles and stars, through rivers and sculptures of time. May your own now be peaceful, your breath steady, your dreams light. Relativity has shown us that time is stranger than we imagined, but also more beautiful, more forgiving. May that beauty stay with you, carrying you softly into sleep. Our story ends here, in a hush as soft as night itself. Thank you for listening, for wandering quietly through time with me. May sleep find you gently.